Hi everybody, we have another vintage equipment teardown. This time it's a Frequency Standards Company Wavemeter, or more specifically a cavity Wavemeter inside this nice aluminum box, model 912-4, and with a frequency range of 900 to 1200 megacycles, because they didn't have hertz back then. So what is a cavity Wavemeter? Well, this thing is basically a manually adjusted analog spectrum analyzer with very limited bandwidth. It only operates from 900 to 1200 megacycles or megahertz, and that's it. If you want something else, if you want a different frequency range, then you're going to have a whole nother box like this designed specifically for that frequency range. So let's have a look at the outside parts of this thing, and then we can pop these 4 screws and have a look on the inside. We've got this nice 50 microamp analog meter right here, RF input into BNC connector, sensitivity for the analog meter low to high, so if the meter at some point starts to peg past the 50 microamp range, then you can just turn it down to lower sensitivity and you can actually get a good reading. After all, it is relative. You're just going to basically tune this thing over here to a frequency, and when this needle gets to maximum amplitude, then that's going to be the frequency that you're tuning to, the resonant frequency inside the cavity, and we'll talk about that in a few minutes. There's an internal external switch right here that hooks up to this crystal output, a couple of banana jack holes right here, and that's just so you can hook up the resonant cavity to a different measuring instrument rather than using this microammeter. You could possibly have something else external that's a little more or a little less sensitive than this thing. Now, like I said, there is a resonant cavity in here, and the dimensions of that cavity are controlled by this very fat micrometer knob right here. So it goes out all the way to a scale of, there we go, 25 and a little bit. For a long time I thought this scale was completely arbitrary, but after some careful measurements just now, I've discovered that it actually counts the number of micrometers, micrometers, microns. It's really, really amazing. So, like I said, 25 number, that's the maximum scale right there. And put that on 40 on here. So we got 2540 and another 0 right there because I got it lined up perfectly. So that's going to be 25,400 micrometers, which is exactly 1 inch, and I measured 1 inch from here to that. The 0 to 25 is just a little bit less than 1 inch, and sure enough, you know, at first I thought it was going to be 40 micro inches per division on here with the 5-digit precision, but it turns out to be 1 micron each. So that's absolutely incredible. 25,000 microns is from 0 to 25, that you can actually get that kind of precision in a mechanical instrument. And I'm not going to go into how you actually read numbers like that on this machine right here. There's, you know, obviously 4 decimal places, 4 significant digits right here, but how do you get the 5th one from these lines? Well, I'm sure there's plenty of other YouTube tutorials and online references that you can check to see how to do that. Up here in the lid is the reference chart. The lid is actually removable here, so we can take this out, get a closer look. You can very faintly see the purple mimeograph ink here from 1956. So this thing is about 59 years old here in 2015, and you can see the original calibration numbers here, frequency megacycles 900 going all the way down to 1200, and the corresponding micrometer readings, which you would expect. And up here in this one, I actually did a measurement probably about a month ago with an Anritsu signal generator. I just did 4 different frequencies right here. We got the 1956 micrometer setting and the 2015 micrometer setting, and you can see each one of these is very, very close to each other, and at most there's 0.6% difference between 1956 and 2015. So this thing is well within spec. The outside components outside of the resonant cavity, they're not going to have any effect on it because it is just a relative measurement where you just measure a peak on the analog meter, and you know all the magic happens inside the resonant cavity. Also in the lid, there's a handy dandy knob with a handy dandy storage space behind the calibration sheet. So I don't know what that's for, just cable storage perhaps. Not entirely sure what it was initially designed for. Okay, took out the 4 screws, and this thing just slides right out of here. Got to move some cables out of the way. Coax cables in here. And there it is. So there's the resonant cavity, the magic box right there. And just the meter, switch, connectors, and just a couple other passive components in there. I should also point out that there is one more component inside this, what looks like an end connector, and it's this thing right here. If I can get that out. Actually, I think this is some kind of a cap. I need to unscrew, or no, maybe not. Just yank it out with pliers. Yeah, there we go. So that's the RF diode right there. 1N21B from Sylvania. Quick look at a data sheet for that diode. Here it is right on the top line, 1N21B, and it's good up to 3 gigahertz. And we can put this thing into a couple of alligator clips with banana jack soldered on the other end, plug it into a diode checker, and what do we get? About 0.37 volts. So as you would expect with an RF diode, it certainly looks like germanium. Now before we crack open this resonant cavity, let's have a look at a picture of what we might expect to find in there. I found this picture online, and I will include a link, of course. This is labeled as a typical cavity wave meter, and this one actually has 2 different inputs. The one that we're looking at right now only has 1 input, but this has 2 inputs because it can operate in 2 different modes, either transmission or absorption. Now the cavity consists of this space right here with this plunger, which moves up and down inside there depending on where the micrometer is set, and that changes the internal dimensions of the cavity, which changes the resonant frequency. If you make the space in here smaller, then it will increase the resonant frequency, or pull the plunger out, increase the volume in there. That makes the resonant frequency go down. Now in transmission mode, you use input A right here. You put your signal on input A, and if the cavity happens to be as a resonant frequency of what the frequency is going in to the input, if those two are the same frequency, then the energy is going to transmit straight through here, through the cavity, and then over to this little loop, pickup loop here, and then go down into the cathode of the diode. And really all that does is it just rectifies the RF energy into DC so that the meter can actually display it. It's just a simple DC 50 microamp meter. We got a few other resistors here for adjusting the scale, and a little capacitor right here just for some DC filtering, I suppose. Now let's have a look at what we're actually looking at with this thing that we're tearing apart right now. I made a few changes in paint and also some pencil drawn changes on here to show exactly what I've seen tearing it down, and that is that the meter actually has, it goes to the wiper of the pot. Here we've got the wiper of the pot for the sensitivity adjustment going straight to the diode, whereas here it goes to the meter, and we still have that other fixed resistor, just a 47 ohm resistor. There's no filter capacitor on this like we have over here, and you probably don't need it because it is just, you know, very high frequency, and it's going to be DC, so that needle is certainly not going to be going back and forth at 1 gigahertz. That's going to be very, very steady with or without a capacitor. Now, the thing that I'm confused with is this switch right here. I said before that these two banana jack crystal output connections, that was for outputting from the crystal rectifier to a different measuring instrument, a different DC current measurement device. But that does not seem to be the case, because the common terminal of the switch is on the DC analog meter circuit down here. So you can switch to the internal cavity, or you can switch to the external something else, some other resonant cavity that operates at a different frequency range, or some other RF to DC source that you can then feed into the meter right here. And I'm just really confused about that, because it seems like that this should be you know, output from the crystal outputting to something else, not output of something else going into this device. Everything else up here is all the same, except of course there's no input D for the absorption mode. It's strictly a transmission resonant cavity device. On now with the teardown, we've got 6 Allen screws here on this end plate and 6 other screws holding it to the chassis. So let's take out these chassis screws first. Here's a closer look at the passives. We got the switch is made of these phenolic boards all stacked and sandwiched together. And then there's some rust on the 10K pot. The 47 ohm has 10% tolerance silver band on there, and the meter is hermetically sealed. As for the micrometer chamber combination, take this off. This is just some tape and cardboard to prevent any accidental contact between this thing and the terminals on the meter down there. And here's a look at the connector where the diode was plugged in there. There's actually a little sleeve that just pops right out, and then there's Teflon insulation in there to you know, insulate the diode from the ground shield all around. And there's a couple of tongs down there that the cathode pin of the diode plugs into. And here's a closer look at the other part of that connector where the anode of the diode contacts it just like that. You can see that it rotates like that with respect to the wire, and it seems like it's all solid brass or solid silver plated brass all the way through, but you can probably just about make out a Teflon ring, Teflon insulation around the outside of that disc. There, we got it to focus. You can also make out right in the center, there's the copper wire, the center conductor of the coax, and some solder around that, and then finally contacting the brass pin in the middle right there. Now here's something very interesting. On the other side of this rather mundane, innocent looking piece of cardboard is some cigarette advertising. Apparently this was on the bottom part of a matchbook, and it's advertising Winston cigarettes. It says right here, finer filter for finer flavor, the carton. That's 1956 for you. I got those 6 Allen screws out. I should point out that there's really nice silver plating on the outside of this. There's hardly any oxidation after almost 60 years, but I think it's going to be a little shinier on the inside. I have not seen this yet. Let's pop the hood. And wow! Oh man, that's impressive because it's so remarkably simple. I was expecting a little more structure in there. It's just a big empty cylinder with a rod in the middle. Incredible. So the BNC input just goes straight down there, the very short little loop that just goes right over to the ground shield. On the other side, we've got the output loop, and that's really just a post sticking up from the bottom there. Let me stick the diode in here. So that's it. The pin of the diode actually forms part of the loop, the pickup loop on there. And then as for the post in the middle, well, that's hooked up straight to the micrometer. I'm turning the handle of the micrometer down here, very slowly bringing it down that way. There's a bunch of little fingers down there all around the perimeter of the rod, just to make extremely good RF contact between the whole tube and the moving spinning rod in the middle. So I got this thing twisted all the way out now. Can very gently pull it out. Don't want to hurt any of the mechanical parts here. It's like defusing a bomb. So there's the thread. I'm sure it's some super precision steel alloy or something like that it's made of. Right there, look at that. We got a three-part thread. The thread, the female part of the thread is just split down the middle. There's even these, what looks like, is it steel or brass? Put a magnet. Oh yeah, that's definitely steel right there. These steel levers that just press down onto the three different thirds of the thread right there to make sure that there's real good close contact and to prevent any kind of backlash. Going back to the outside handle of the micrometer, there's this clear plastic cover which covering what looks like to be a screw, just an Allen screw that attaches the whole rod and the thread to the aluminum cup. And there's a little set screw right there which pokes through the other side, sticking up just a couple millimeters, and that would make contact with this little notch sticking up there. It's nice smooth all the way around until right there. There's that little notch sticking up, and so that would be the point where this thing stops turning and you don't push it in too far and cause some kind of damage. There are 3 brass screws that I took out right here, so let me just dump those out. And then we can see that there's another notch right down here on this, on the cylinder that just pops into there. There's nothing here for that notch to make contact with. I have no idea why they would have it there. Maybe for some other kind of construction in some other smaller apparatus or smaller micrometer mechanism. Not entirely sure. Actually, I think I do know. I know exactly what that's for. That would be for the option of possibly having a set screw or some kind of pin going through the shaft right here, and then when this thing gets unscrewed all the way out to the maximum scale, then you eventually reach a stop, and that screw would prevent anybody from accidentally pulling the whole thing out after you unscrew the whole thing out of the thread. So basically this notch keeps it from being pulled out all the way, and this notch keeps it from being tightened down too tight. 6 more screws out of here. Let us take off this back plate which fits down inside the tube. And what's really interesting about this is that it looks like the smokestack from a mid-19th century steamship on the mighty Mississippi. Really, really nice little fingers there to grip the center conductor. And there's a little fork that the diode plugs into, just like that. And we can take this thing down even further. I unscrewed the 4 screws from the BNC connector, and then we can get a real close look at the little loop right there, just going straight from center conductor down to a welded or perhaps a brazed connection right down there to the shield. Also, there seems to be some kind of remnants of glue or epoxy where the end cap fit into the big metal tube, and I'm not entirely sure why or what it's even made of. It might be some kind of super conductive, super concentrated with silver stuff, and it's very, very dried up. Oh, I can scrape off a tiny piece right there. There we go. Maybe I can poke it with a meter and see what we measure. Alright, let's see if I can do this. 1 contact and 2 contacts. Did I just break it? Yeah, I just broke it. Let's try that again. Wow, 0.4, 0.3 ohms. So yeah, that is super conductive, as you should expect for RF applications like that. It must be some kind of paste that's very concentrated with silver, and they just use that to fill any kind of gaps in here between the outer tube and the end cap. Just got to make sure there's plenty of conduction all the way around. On the other end though, where we first opened it up, there are no such provisions. Just straight up silver to silver contact right there, plate to tube. I was actually expecting to see some kind of O-ring made of silver plated brass fibers going around here, but no, it's just contacting just like that with screws, and they're just ordinary steel anodized screws. No big deals there. I have no idea how the RF energy gets transmitted from one end to the other, but I would suspect that they didn't bother with any kind of extra conduction or super good closure over here, because maybe there's a null point in the RF energy, the electromagnetic field, a null point, a node really right here on the end plate. So not much happening there, at least at resonance. There probably would be a node right here, and then everything else. This is the business end. That's where most of the RF energy is going to be, down here on this end of the tube. As I put this thing back together, I just want to reiterate something that I briefly stated in another video a couple years ago, and that is whenever you put a screw inside a threaded hole or a threaded insert, especially if it's plastic, if it's already a pre-threaded plastic hole, you always want to make sure that you rotate the screw counterclockwise first. Keep going until right there, when the screw just pops straight down. If you hear it or see it or feel it, then you know that the threads are locked, and you can just go right in there and tighten the screw without any danger to damaging the threads on the screw or the hole and causing irreparable damage. I got the resonant chamber back together now, and that's the only thing that I'm going to put back together. I even took the coax cable off of this connector right here, and I just want to keep this as a nice silver plated bookend. That's pretty much just a heavy bookend. That's all it's going to be for now, but eventually I might use it as some kind of a real fancy project box of some sort, some nice elegant artsy fartsy project that I might want to work on, be it electrical, mechanical, or just purely for artistic value. I have no idea, but I want to keep this thing whole for now. And I got a few other parts out of here. A nice 8-inch coax extension cable, a couple of female banana jack connectors, double pole or a single pole double throw switch, chicken head knob, and a real nice 50 microamp DC microamp meter from Rollersmith, Bethlehem, PA, very, very close to where I grew up in the Lehigh Valley. One thing I won't be keeping is this piece of crap 10K pot right here. It's all rusty, 10% tolerance resistor. Certainly don't need that. I actually measured the pot and it came out to 11,300 ohm total resistance. The 47 ohm resistor was more like 49 ohm, and the meter itself 2,160 ohms, and that lets us figure out the real current range for the high and low scales. So if we assume 50 microamps going into the meter, then on the high sensitivity setting all the way on that end of the pot, we're looking at 60 microamps total that the meter will be displaying. 60 microamp for the whole system here with the shunt resistor in there. Or low sensitivity, we're looking at basically 2.25 milliamp full scale that this thing would be showing when it's fully deflected all the way at 50. It'll be really 2.25 milliamps instead of just 50 microamps. Another thing about this micrometer instrument, I was hoping that I might be able to use it as a real live micrometer and put it in some kind of apparatus where I can measure depth or distances all the way down to 1 micron precision, but that's certainly not going to happen because, as we saw before, it's just a brass rod going through there, silver-plated brass rod, and that is going to be very susceptible to temperature expansion variations, and certainly not useful in that respect. It'll always have the 5 significant figure precision with all this going on here, but it's definitely not going to have very good accuracy. And on that note, if you do take temperature into account, then temperature is probably not going to affect the overall performance of this as an RF resonant chamber, because as temperature increases, the rod in there is going to expand just a little bit, but so is the rest of the chamber. It'll expand all in equal proportions, and it'll probably maintain the same kind of RF resonant frequency in there. And the second reason why I decided to not put this whole thing back together is because of the box itself. I want to keep the box because it just happens to have something fit in it very well. This is pieces of a project that I started working on more than a year ago. I was surprised because it didn't feel like more than a year, but I checked the video that I posted back in June of 2014 about this Numitron clock that I started working on back then last summer, and I think I said I would have it done in a month or so, but it's been 14 months now and still I haven't had much progress since then. And it just so happens that the whole thing will fit in here very well. Of course, I'll have to, once I finish it, I won't have these wires sticking out the end. And I will also need to remove this top lid here, this hinged storage chamber thing, get rid of that, and then the whole thing will fit extremely well, minus the tubes, of course. The tubes I can just stash down there, and probably just stash the whole thing in there for me to finish it at some later date, because after a whole year I just haven't done anything with it. And that's the end of that. We got a lot of awesome parts and information out of this whole project of tearing down this RF resonant cavity wave meter. I'm surprised that there isn't a whole lot of information out there about these cavity wave meters. I mean, a quick Google search certainly yielded something like this and a bunch of other pictures similar to that. But as far as any specific models of cavity wave meters being shown or torn down or anything like that, I didn't see much of any information out there at all. So I'm glad to have actually done this and put this kind of information out there. I can probably boast that this is the most comprehensive look at the inside workings of a cavity wave meter on the entire internet. And I learned a whole lot while tearing this thing down and researching it. And if you learned something too, then please give this video a thumbs up, and I will see you later in another video. Thanks for watching.